This is Nanoscape. I'm Seth Zimmerman.
And I'm Erin Spain.
On this show, we venture into the frontier of nanotechnology
With experts in the field who are turning the science of small into the next industrial revolution.
This podcast is brought to you by the International Institute for Nanotechnology at Northwestern University. Today's guest, Roel Templaar, is a Northwestern University chemist whose lab aims to unravel the mysteries of quantum mechanics and their impact on the properties of emerging materials.
We welcome him to the show today to talk about the ever-changing field of nanotechnology and how his work sits at the cutting edge of nanoscience, advancing the basic understanding of chemistry and physics at the nanoscale.
Welcome, Roel. Thank you for joining us.
Thanks so much. I think it's great you're doing this podcast, and I'm excited to be part of this.
We are happy to have you here, and we want to get to know you a little bit. So you are originally from the Netherlands. Tell us about your path from there to Northwestern.
Oh, sure. Happy to. I lived the first half of my life so far in the Netherlands, a little more than that. I did all my academic training at a really nice place, University of Groningen, this place that some people like Ben Veeringa are coming from, that are well-known folks around here. And one thing I want to emphasize that I think is quite curious and worth mentioning is that at the University of Groningen, we have a center for advanced materials, which is actually suspiciously similar to the International Institute for Nanotechnology. And so
we have some fans over there, maybe, no?
Maybe mutually. And so in a way, coming to Northwestern felt a little bit like homecoming to me.
Oh, that's so nice. And you mentioned, so you knew about Northwestern during your time as an undergrad and doing your graduate training. This was a destination for you, perhaps?
It would be a bit of a stretch to put it that way. I did know of Northwestern, and the reason I knew of Northwestern was because of George Schatz. And to be very honest, not so much necessarily the details of his theoretical work, but I knew him as the editor-in-chief of the Journal of Physical Chemistry. And so that, for me, put Northwestern on the radar. But of course, as I progressed in my academic career, I got to learn more and more about the phenomenal research that's being performed at this university. And once I was applying for jobs, having the opportunity to interview here was really, a dream.
So when did you really first become interested in chemistry? This is something I'm always interested in. Everyone has like that moment where it just kind of clicks. Like, this is it. This is what I want to do. What was your moment for you?
To be honest, this is a bit of a loaded question because I didn't really like chemistry at first all that much, at least at high school. And don't read too much into that because everybody knows that high school chemistry is not the same as pushing the frontier of chemistry in academic research. But no, I actually pivoted towards physics at first. And so my entire undergraduate and also graduate training was actually in physics. But the way at the University of Groningen, the departments were organized was again very much dictated by this Center for Advanced Materials that I mentioned before. And this is again where I want to draw on the parallel with Northwestern University, where the culture was very much cross-boundary. It was very hard for me to pinpoint for various professors which department they were even in, because everything was sort of put together within this materials-oriented institute. And so even though I thought of myself as a physicist, I, unbeknownst to myself, drifted into chemistry research. And as soon as I started to cross the Atlantic and got engagements at American universities, I suddenly found myself in chemistry departments, and I realized that it was actually chemistry that I was passionate about.
So today, how do you explain to people, maybe they're a non-scientist, what it is that you do?
It actually very much depends on the person. And by and large, I have two versions of this story. One is a somewhat practical applied story in that I intend to contribute through theoretical research to propelling new materials, new nanostructures, new molecules in order to harness phenomena in an entirely new way that open opportunities for technology, healthcare, etc. And this is reflected by the various collaborations that my group has with various experimental labs within the chemistry department, other departments in Northwestern, and even beyond. And the other story is more of a, fundamental story about the mysteries of quantum mechanics.
Ooh, I want to hear this, yes.
Exactly.
All right, I'm ready.
Quantum mechanics is about 100 years old, a little over 100 years old, depending on where you draw the line. And on one hand, we have learned a lot about quantum mechanics, and it's widely accepted to be a foundational theory of pretty much everything that's going on in chemistry and lots of physics as well. At the same time, there are still many unresolved questions related to the foundations of quantum mechanics. Quantum mechanics is a counterintuitive theory. It is also a complex theory in that it can give rise to many unexpected behaviors that depend non-trivially on the interacting ingredients of your problem. As we are also propelling new technological advances, my group is also very passionate about unraveling the mechanistic principles of quantum mechanics. And that's an extremely exciting line of research that puts us in, I would say, in a direct lineage, tracing back to, let's say, the early 1900s, all the developments that happened in the 20s, in the 60s, 70s, 80s, 90s, and this is ongoing. So that's something that I think is incredibly interesting. And, I think it appeals to a lot of people as well.
That word quantum, it conjures up a lot of thoughts for folks, and some people might not even really know what it means. So what are some of the biggest misconceptions that you like to clear up just with the public when you're talking about that?
Not us, obviously.
Oh,
we both fully know what
100%.
it's for everyone else who might not.
100%. This is a tricky question for me because, I don't hang as often in public spaces talking about quantum mechanics as I wish I did, perhaps. But I can imagine that one of the misconceptions about quantum mechanics is that it's an entirely uncertain theory, that it is not deterministic. This is in a way true, but in another way, it's also not true. And so, as you may know, quantum mechanics is a lot about uncertainty. It's about Schrödinger's cats being dead and alive at the same time. And so, in a way, quantum mechanics is very much about uncertainty, the reality that you never really know what you have. But at the same time, the probability distributions that govern the outcome of any probabilistic measurement are actually governed by dynamical equations that are entirely deterministic. And in that sense, we can build a fully deterministic framework with which we can steer probability waves in a fully deterministic way and have them interact and interfere with each other in a fully deterministic way so that we can design exactly the outcome that we want to have. And I think that's a potential misconception where I can see where some may come in and say well, quantum mechanics is all kind of uncertain and you never really know what you're getting. But at the same time, it's providing us with this very solid foundational principle that we can use in engineering to get devices that behave exactly the way we want them to be.
That is a very good explanation. Thank you for that.
You're welcome.
Is it true that you consider becoming a professional jazz pianist?
I have considered becoming a professional jazz pianist. I don't know if it was a reflection of me being that good or whether it was a reflection of some naivete I may have had. That's really hard to tell. It's almost like a quantum measurement, sort of doing a self-reflection there. I would say that the point that I was genuinely thinking about becoming maybe a musician was probably towards the end of high school. And that's, of course, a very natural time for you to think about will I become a football player or maybe a jazz musician or maybe a professor, right?
The big three. Yeah.
Exactly. I think I made a strategic decision. It's been a while, right? But I think I made a strategic decision where I thought by myself, let me study science and I can continue playing and maybe I can see how far I can push that combination. And so I did. So during my college years, I did play a lot of piano, a lot of music, and that paid in part for my college and things like that. It was kind of like a side job. It was really a nice experience. What I think was a monumental experience for me as well was towards the end of my PhD, I got an offer to go to New York City to work in the lab of David Reichman at Columbia University, which on one end is a phenomenal academic opportunity that I took with both my hands. But on the other hand, it gave me the opportunity to spend a couple of years in what is the mecca of jazz music.
Mm-hmm.
Absolutely.
Exactly. And, one of the considerations that I had going on was, I'm going to be more and more busy as an academic, but will I compromise the music? And I decided to keep that going as much as I could. And I'm really glad I did because New York turned indeed out to be this phenomenal environment where I could really develop myself as a musician as well as an academic. And I'm really glad I got to have that experience.
I mean, Chicago's not too bad for a jazz scene either. Can we see you some night at the Green Mill or where might you be?
Well, maybe it's in incognito fashion. If you Google my name these days, with jazz, you don't find a whole lot. No, actually, let me tell you this story because it was kind of formative and it's interesting to me is 3 things happened at the same time, more or less. I started my new job at Northwestern in early 2020. Maybe four things happened. We also just had our first baby or daughter, and then COVID also happened. So I have to be honest, I moved to the Chicago area kind of with the idea of like, yeah, wouldn't it be fun to continue playing? But the culmination of these three things, I was pretty busy with my job.
Yeah.
I had this baby.
That's a lot.
A lot
Yeah.
at once. Yeah.
And so here I found myself, sort of being in the scene of New York and having a great time to being here in Evanston under COVID lockdown,
With a new
nothing
baby.
going on. Right. And it was an interesting experience because I was trying to figure out, okay, who's to blame here? Is it me being busy with a new job, or is it COVID, or is it having a baby? And I think the culmination of that made it a really organic, natural transition where it's like, yeah, oh no, this is completely impossible. It's not like it's a little bit impossible. It's just out of the question. And so once COVID lifted and, the kids are getting a little older, I'm very much interested in, keeping the music going. I'm just rehearsing, playing for fun. Who knows? Maybe one day you'll see me somewhere.
Did this musical background, does it influence your research, your approach to how you do things?
Absolutely. 100%. I mean, this sounds cliche maybe, but I have benefited from this tremendously in an incredible amount of ways. I think the most important aspect, especially of jazz music and performing, is dealing with uncertainty. Because performances are improvised, there is some sort of backbone. Like when I think, okay, we're going to play Misty tonight, it means we're going to play Misty. But how we're going to play it, how fast we're going to play it, whether we make it a samba or a bossa or a swing or a ballad, there's so many things you can do, and it all comes together in a moment. And so one of the things I learned from performing is to show up, put myself in a certain mindset where I have no clue what's going to happen in the next 2 hours, but it's in public, there is some pressure, and to kind of trust that you'll figure it out by improvising. That skill, I think, is incredibly important in many aspects of science, including research, including collaborations, but also including teaching and presenting. For example, when I prepare myself for teaching general chemistry class in front of 180 students, I think the experiences are very similar. Like you kind of prepared your class in a certain way, but you're always underprepared because you always have to juggle all these things at the same time. But to kind of trust that you'll figure things out as you go is a really important skill that I think I've developed quite strongly during those performance experiences.
Being in front of a lecture hall with 100 and some college students makes me feel really nervous right now. You really do have to know how to read the room and keep their attention. Yes.
And again, I kind of like the uncertainty now. It's something that I enjoy. It's like, I guess, improv comedy or whatever, which I don't know much about. But like, there is a certain appeal to being able to surprise yourself. Keeps it interesting.
So let's talk about your lab. How would you describe the goal, and how exactly does it intersect with nanotechnology?
This is kind of tying into the answer I gave earlier. I think this is really a philosophy that I think is running through my lab, where the goal is in a way twofold. On one hand, it is to really help propel advances at the forefront of nanotechnology, material science, chemistry, and physics, in collaboration with experimentalists, engineers, telling them what to build, what to measure, what would come out of these measurements, how would this tell us about emergent phenomena that help us propel technology. On the other hand, there is this fundamental curiosity-driven desire to advance our deep understanding of quantum mechanics. I would say more broadly, the physics playing at the nanoscale when you have a non-trivial combination of components all interacting with each other. The efforts in my group are mostly centered around trying to hit those two birds with one stone. I try to really set up the individuals in my group on projects that are really at the intersection between important developments on the engineering and experimental and devices, if you will, side of things. But at the other hand, it's very much driven by fundamental questions. And one way to put it is that if, let's say, a project is so much in the mainstream of our well-trodden understanding of a phenomenon, I would be less enthusiastic to pursue that, even though it could serve, developments in engineering and experimentation. I'm really seeking to find an intersection where we would at the same time also learn really important deep lessons about how quantum mechanics works, how just dynamical phenomena in general works, and the physics as well. For as much as my group intersects with the IAN, I think this is a perfect combination, because the IAN, I think, is very much about interfacing between societally important developments, technology, healthcare, all this sort of things, but at the same time keeping that connection going with the deep fundamental questions. And so I think we're very much the theoretical embodiment of that.
Well, and you are doing this. I mean, some of your recent findings have really challenged textbook principles. Tell me a little bit about that. Some of your work in chiral light matter interactions, for example.
I would make a little correction to that somewhat broad statement because that's very bold. What I shall say is, and I want to emphasize this because I think this is the first time I've ever been in that sort of situation where we really stumbled upon a finding that was apparently defying what you can find in textbooks, which I think is incredibly exciting. It's a textbook principle held strongly in inorganic materials and maybe in material science in general, is that for a material to be able to absorb circularly polarized light, that material cannot be centrosymmetric. And we have made a theoretical prediction that it is in fact possible to come up with centrosymmetric materials that do so. And not only that, we have collaborated with Ken Poppelmeier here at our department and also with Randy Goldsmith at the University of Wisconsin at Madison, where we essentially predicted, designed, and measured a centrosymmetric material that indeed did absorb circularly polarized light. And so this is something, again, that to me is an incredible experience because it really puts us right at odds with what you can find in a textbook. Now, you may be wondering, well, was the textbook wrong? And the answer is yes and no. It turns out that the conventional physical mechanism through which circularly polarized light becomes absorbed in materials, that mechanism is indeed impossible for centrosymmetric materials. But what we have recognized is that there are various other ways, physically speaking, in which circularly polarized light can be absorbed in materials. And that one of those mechanisms is indeed allowed in centrosymmetric materials. Once we made this theoretical discovery, the first thing we, of course, did as a theory group was to look in the literature and see if we could find any reports in the literature at all of any centrosymmetric material that was measured to absorb circularly polarized light, and we couldn't find anything. And so we think very strongly that we indeed are showing this for the first time, not only in theory, but also in experiment.
Very exciting. That's very exciting.
So some of your other recent publications have been about hybrid light matter states and quantum. We're back to the quantum.
Yep.
Quantum classical simulation of materials. So where does that fit in and where's that kind of going?
Yeah, let me tackle both parts of this, starting with these hybrid light matter states. I think this ties into nanotechnology at large, really from the perspective of that at the end of the day, what we want to do is we want to bring together different components, have them interact together in order to give rise to new states, new sorts of dynamical phenomena that we can control and that enable us to perform tasks that we couldn't perform before. And turns out one of the ingredients that we can play with is light. And maybe the counterintuitive part of that, light is oftentimes seen as something that's not material. It's non-matter. But it turns out that if you create nanostructures, you start to automatically confine electromagnetic fields in nanoscale cavity-like structures. And if you do that close enough, you start to see quantization of optical fields. And these quanta of light that you get for free, you can use those components as it were additional components of your material. You can start to have them interact with electrons and nuclei in order to create new states of your material that you can start controlling. This is a pretty active field at the moment. There is a ton of activity going on at the intersection of chemistry, physics, and material science at large. Our group is specifically interested in contributing to this line of inquiry, focusing on chirality. So you can see chirality is a little bit of a thread running through my group, and we've been particularly interested in seeing how we can use quantized state of light in a matter context, particularly focusing on the chiral states associated with these quantized optical fields.
Well, your accomplishments are being recognized. You were recently named a Sloan Research Fellow. Tell us about that, what that award is all about.
First of all, it's a great honor, unambiguously. Being named a Sloan Fellow is a form of recognition that I think is very direct by the community. It's extended by experts in the field who care deeply about fundamental science. And so having that recognition really means the world to me. By the way, not only to me, but also especially to the talented students and postdocs in my group who, of course, are actually doing the work.
Nanotechnology is an ever-changing field. So what are you most excited about? What things are happening out there, not just in your lab, but in the greater nano landscape? And how is your research really kind of fitting into all that?
I think the thing I'm most excited about is how we get better and better control of quantum mechanics, even at larger scales and at longer time scales. The way quantum mechanics is oftentimes presented is that it's something that governs the atomic scale. It's something that allows you to explain a hydrogen atom and its absorption spectrum. But it's something that at large scales washes away. And I think, you can come up with a legion ridiculous examples of macroscopic objects like a chair or a cat that are decidedly classical, that are not quantum mechanical. And in a way that's true, but I think a really exciting opportunity that we start to see emerge now, and this is tying into this so-called second quantum revolution that's happening as we speak, is that we become more and more prolific at producing quantum systems that become bigger and more complex and that last for longer and longer times. This is, of course, tying into things like quantum computation, where you want to build entire quantum networks of qubits interacting with each other, quantum memory, and all these sorts of things. This ties into diagnostic tools where we want to use quantum effects to essentially diagnose healthcare-related things and so on. Now, this very much ties into nanotechnology, because in order for us to build the environments in which we can engineer quantum phenomena at larger scales and longer time scales is through detailed control at the nanoscale of hierarchical systems, so to speak. And so this requires us to have precise control across a vast hierarchy of length scales, but at the bottom is nano, right? So if you screw up the nano part, there's not going to be any quantum permeating through that layer, right? And so I think that's just a phenomenal challenge, and I'm really incredibly excited to see how far we're pushing the envelope at the moment. And again, for us as a theory group to contribute to that in also pushing theories to larger and larger scales while retaining quantum predictivity is really something that makes me incredibly excited.
So as you mentioned, in some ways, you're just getting started. Talk to me about the next 5 to 10 years. What would you like to see happening in your lab? What could we expect from your group?
Let me elaborate a little bit on some of the thrusts we have running, because I've really deliberately organized thrusts in my group with a long-term goal in mind. So one of the thrusts is something that Seth mentioned, and I haven't really gone into that too much so far, is how we can harness mixed quantum classical theories and models to describe materials. Well, let me put it this way. The advances made in materials engineering are really incredible at the moment. And especially our ability to control and engineer dynamical behaviors of materials is really going at an incredible pace. At the same time, these developments pose a very notorious challenge for theory, because in order to describe something as large as a material, quantum mechanically, for a long duration of time is really challenging. And so the solution that we have in mind in our group is to embrace partly classical models, which are much more tractable and easy to solve than quantum models, replacing quantum ingredients by classical ingredients in order to be able to describe the dynamics of materials. This may sound a little arbitrary, but we have very well-informed ways of doing this, building on many decades of prior research. And we're now starting to see successes. So we're working on a manuscript right now where we look into so-called spin valley depolarization mechanisms in atomic monolayers. This is a decidedly quantum phenomenon that we can describe using mixed quantum classical equations of motion. We're doing this now for one particular material. This is like a prototype study that we do, but our aim is to build this into a big program that I think is transformative to the field. And this is one of the things that I'm excited to look at in the next 5 or 10 years and build this up in earnestness, and I'm really excited to see what that will yield.
Is the quantum realm a real place? I have to know.
That question can be very deep when you think about it, and I tend to sometimes have, not too often, but sometimes have philosophical conversations about, like, is quantum mechanics even real? That's one interpretation of your question, so I'm going to address that first, and then you can ask further if you need further information. I think what's really incredible about quantum mechanics is the predictions it can make, right? What sometimes is a little eerie about the work that we're doing is that it's all very abstract, and you can't really... We're solving mathematical equations, sometimes on paper, sometimes in a computer, right? But the phenomena that we describe, you can't see. So you even can go to the experimental lab and say, okay, well, these theorists have predicted this and that. can you measure it? And then they would use spectroscopy, but no one really can, with their own bare eyes, see anything happening. So everything becomes this kind of philosophical question of like, what is reality? Is any of this real? And I think you can completely bypass that philosophical question once you start look at what we can do in terms of predictions, the devices we can make, the smartphone in your pocket. That's all the product, more and more so, of quantum mechanics, right? And of the things that we are doing. I would say the smartphone of the future will be building on the things that we're discovering today. And that's, I think, a testimony of the value of quantum mechanics, theory, spectroscopy, any of the nanocentric scientific things we have going on in the Western and beyond. To me, I try not to get too much hung up in the question of like, what's the quantum realm? Does it exist? Because I can tell you, you can go down that rabbit hole. And I can also tell you that quantum mechanics is not a complete theory. There are unknowns in quantum mechanics, for example, the Copenhagen interpretation, that we still haven't figured out even after 100 years. But I think none of this is a reason to stop what we're doing. Look at what we can do with it. And these questions are spectacularly interesting in their own right, but you have to also protect yourself from not getting too lost into them.
I also went down a bit of a rabbit hole when I was preparing for this one. So I read that is photosynthesis considered a naturally occurring quantum process? And if so, kind of what lessons from nature do you think could really inspire new nanotechnologies?
That's really a great question. I think the answer at large is yes. It's decidedly quantum mechanical for trivial reasons that it's a molecular phenomenon. It's at the small scale, and much of it is governed by quantum mechanics. And to add on to that, there is a lot we can learn from it as well, because nature has had billions of years of evolution to essentially optimize a process to its current form, whereas we're just the babies, the newcomers, trying to build devices that kind of do the same thing. There are a few caveats. One is that quantum mechanics is highly non-trivial. And so what we mean by quantum and how, what flavor of quantum exactly governs photosynthesis is up for debate. And these are debates that are still being held. At the same time, in our endeavors to replicate and be inspired by nature, we have to also bear in mind that organisms have a whole lot of different priorities that they have to juggle at the same time, one of which is the preservation of their DNA, or in other words, like they have to worry about offspring and, continuation of their particular life form. If you look at a photosynthetic complex, having in mind the plan to build a solar cell, then you have to realize that the solar cell may not be juggling the same priorities as the organism has. And so some of the mechanisms in place in biology are informing on how you should build a solar cell, and other mechanisms are distractions for your solar cell because they're merely in place to protect the organism for certain things that you're not so much interested in for your solar cell. I can say I've interacted with the community on photosynthesis research to some extent, and I think this is an incredibly exciting line of inquiry, and it's very rich, and there are many aspects that you have to sort of take into consideration to really make sense out of it.
Well, Roel, thank you so much for coming on the podcast. It was great to hear what's happening in your lab, some of the things we can look forward to, and we're looking forward to having you here at Northwestern for many years to come.
Thank you so much. This has been great fun, and I'm excited about this podcast, so I'm looking forward to all the future episodes you guys are working on. I think it's very exciting.
Thanks so much for listening. This podcast is brought to you by the International Institute for Nanotechnology at Northwestern University. Be sure to follow this show on Apple Podcasts or wherever you listen to podcasts, and be sure to give us a 5-star review.
For more information about IIN, go to our website, iinano.org/podcast.